Welcome to the video. In this video, we are going to find all critical connections in the graph. So you may understand critical connections as the choke points or the articulation points. If you remove that particular edge, the, the graph will become disconnected. The graph will become disconnected. Okay, to see in example 1, you have three edges, 0, 1 and 2. Okay, now if you remove 0 on 1, see this, okay. If you remove this one, now they will be disconnected graph 0 2 and 1, two graphs. If you remove 0 2, okay, then they will be just they will it will from one graph it will get connected to two components, that is 0 1 1 and 2 as a singleton node. See with example 2, 0 1 2 3. Okay, if you remove 2 and 3, there will be two components, 0 1 and 2 and 3 as a singleton node hanging around. Okay, so this question is same as finding bridges. Okay, finding bridges. Okay, using the Tarjan's algorithm. Okay, so in Tarjan's algorithm, okay, I will just say what we'll do. We will find the critical connections which are also called bridges in this given undirected graph using Tarjan's algorithm. Now for finding strongly connected components, okay, now we will assign discovery times and lowest reachable times, okay, to the vertices, and we will identify bridges by comparing these two values, these time values, okay, during the DFS traversal. Okay, so what we will do, find strongly connected components, we'll apply Tarjan's algorithm, we will apply DFS. Okay, now let's see what we do. First of all, this the basic condition. If you're doing in Python, you have to write these two lines. You have to increase the recursion limit, otherwise it will fail and you won't be able to understand. It will give you random error. It will give you like you are getting runtime error, but it should give TLE, but it won't give you TLE. Okay, it will give you runtime error. Just add these two lines and it should be 9. I mean, I gave 6 7 8, but it didn't work. Okay, so I increased the recursion limit. This is not the optimal way, but you should do this turnaround. Okay, first of all, I will create a list discovery time for initialize it with -1. Then lowest time. Just remember I told you two times. -1 for I in range. Again, again, the current time which we will use, the current time. Okay, okay. So and then an empty array called bridges. We'll return all the bridges, and we have to return in the sorted order. Okay, a particular bridge should be in sorted order, and all the bridges altogether should also be in the sorted order. So I will tell you what I did over here. I initialized two arrays, discovery and low. Okay, both of size v. Okay, which is the number of vertices in the graph. Okay, now this discovery. Okay, this discovery will store the discovery time of for a particular vertex u. Okay, discovery u we will use. It's not okay. I did some mistake. Okay. And now this particular low will store the lowest discovery time reachable for vertex from vertex u. Okay. Okay. Now we initialize the time to 0, which will be used to assign discovery times. Okay. As we go ahead in the DFS traversal. Okay. Now we will apply our Tarzan's algorithm to find the strongly connected components. Okay. Two parameters, particular node u, and a parent. We will initialize it with -1. Okay, -1 means it is not visited, but if it is not -1, it is visited. Okay, now first of all, the discovery time we'll need to open discovery times. Discovery time will be self dot time, and low you will also become self dot time. With so to begin with, we will initialize the current time, the self dot time in the discovery of node u and node v. Again, increment this time by 1. So what we did, we set the discovery time and lowest reachable time for the current vertex u. Okay, now we will iterate, okay, through the neighbors of v. Okay, v for v adjacency u. Okay, now we will iterate to the neighbor, all the neighbors. We are the neighbors of at this vertex u. We will iterate to vertex u, and we are all the neighbors. Okay, now if v is already a parent, v is a parent. Okay, if v is a parent, we will have to skip it. Okay, just if v is parent, skip it. If it is not a parent, if it is not a parent, okay, but discovery v is already is -1. Discovery v is -1. When it is -1, it is the beginning. Okay, now discovery v is -1, which means this particular neighbor has not been visited, because we initialize with -1. And as we go ahead, as we discovered, as the particular neighbor gets visited, particular node gets visited, we will change its time. Okay, as we did here. Okay, but if it is already -1 after doing it, this means it is not already visited, it has not been visited. Okay, if that's the case, I will recursively call this strongly connected component function. Okay, strongly connected component function. Okay, and current the current node will become v, which is the neighbor over here, and u will become the time. You will become the parent. Okay, node particular u will become parent because we came into v from the u. Okay, so u will become the parent of v. Cool. Now change the time. Change the lowest possible time. Lowest possible time. Lowest possible time between the lowest possible time of parent and lowest possible time of its parent or a child. Okay, particular node or its parent. Now No, now the main condition, because it was given over here, if there's a bridge between 1 and 2, we'll have to return as 1 2 and not 2 1. Okay, it will give us error. So we'll check if particular low v is greater than discovery time of u. The lowest time of v is greater than discovery time of u, and if v is greater than u, bridges depend. Remember, v is greater than u, so v should come after u. In this case, uv. Else, if v is smaller than, then bridges dot append v comma u, because since v is smaller than u this time. Okay, now if we were doing, if this particular neighbor has, if this particular neighbor node is not already visited, but what if it is already visited? What if in the case it is already visited? If it is visited, we will just see, after we recursively called our strongly connected component function, we just change the value, we just change the value of lowest possible time value of this particular node u, parent u. Okay, now if it is already visited and it is not -1, okay, in that case we will replace its value by low u, or the discovery time of this neighbor. Okay, okay, now either the lowest possible will be this particular lowest possible time of its parent, or the discovery time of its this particular neighbor. Okay, discovery time of its particular neighbor. Now after we have calculated everything, okay, remember we are doing in self, so it is just depends on call and it won't return anything. Now we will call this particular strongly connected component recursive function for all the vertices which is given in this input array. Okay, now input adjacency list. Now if discovery time is -1, if discovery -1, which means it is not already visited, if it is not already visited, call the recursive function. Okay, and after that you have received everything, just dot sort and return the bridges. Let me submit it and check how far we have came, how close we have came. Okay, yeah, it did the job pretty effortlessly. Okay, now this time it is taking very less time. Other, if I would have changed, if I have decreased the recursion limit, it will very possible it won't get solved. Okay, so I hope you learned a concept and enjoyed this video. I will attach a Medium article wherein I have explained this concept in more detail in the description. You can go there. Okay, okay, so thank you, have a nice day.